Hello and welcome. What you are looking at is a standard two-stage reduction gear comprising of the motor, first and second stage gears, and the output. Normally you would use planetary gears, but I'm using two coaxial magnetic gears. I will add a link in the description to how these individual stage magnetic gears work. But as you can see, a two-stage gear takes the input from the motor, steps it down through the first stage output connects to the input of the second stage, and the second stage again reduces the speed to the output. The spirals on the output are simply there as a nice visual demonstration of the output speed. But why bother with multiple stages if a single stage is so simple? One of the reasons is torque density. In other words, the maximum Newton meters that a gear can transmit per kilogram of weight. The research paper by Gardner, Johnson and Hamid shows that torque density decreases with increasing ratio, and that a single stage gives you the optimum torque density up to ratios of 10 to 1. Between ratios of 10 to 1 and 100 to 1, it's better to use two stages, and between 100 to 1 and 1000 to 1, it's better to use three stages. There is a special two-stage gear called a compound differential gear, which promises better torque density than a three-stage gear, between ratios of 100 to 1 and 1000 to 1. I will be using these same components, so let me explain what we have here. The first stage has a ring gear with 18 magnets and a pinion with 12 magnets. The modulator ring houses 15 pole pieces, iron pins, and also acts as the fixture to the base. The second stage has a ring gear with 24 magnets, a pinion with 18 magnets. The modulator ring is the output with 21 pole pieces, and in this case I've strapped the ring gear to the base to act as the anchor. The first stage is anchored by its modulator ring, and since the magnet ratio is 3/2, the ring gear has an output reduction of 3/2. The direction of rotation is opposite to that of the input. The second stage has a magnet ratio of 4/3, but since the modulator is the output, that gives a stage reduction of 7/3, and the direction of rotation is the same as its input. The total combined reduction is therefore 3/2 times 7/3, and that's a reduction of 3.5 to 1. Let me show you what it looks like inside. I'm going to disassemble this second stage. There you can see the ring gear, the modulator pins, and the pinion. The pinion is mounted on a recessed bearing inside the modulator ring. You can see that it works in reverse. If I hold the ring gear and turn the modulator ring, the pinion spins quite fast. The same happens at the first stage. The pinion is mounted directly on the motor shaft, and these pole pieces are embedded in the base. Before I reassemble the parts in the new configuration, let me show you where I got the idea. This research paper looks at multi-stage gears and torque densities specifically for magnetic gears. And towards the end, they propose this peculiar arrangement. It is supposedly capable of much higher gear ratios compared to a standard multi-stage gear with similar stage ratios. They also mention something about internally circulating power, which is something I've never encountered before. So I built one to see for myself. In a nutshell, the individual stage gears are no different from before. The first stage is anchored by its modulator ring, but it's in how the second stage attaches to the first stage that makes this unique. The rotors are connected directly to each other. The pinions are both mounted directly onto the motor shaft, and the second stage has no direct connection to the base. I add a small hex coupler to the rotors, which will engage the hexagonal socket, and the pinion simply screws onto the threaded shaft of the motor. Now look what happens if I turn the input at the motor side. there's a marked increase in the reduction ratio. I can calculate the total ratio by once again taking the product of the stage ratios, and that was 7/2, and this time I divided by the difference between the magnet ratios of these two stages. This had a magnet ratio of 1.5, stage 2 has a magnet ratio of 1 1/3, the difference is 1/6, so I need to multiply the 3.5 by 6, and that gives me my 21:1 ratio. I selected this very modest gear ratio simply as a demonstration model. I don't want to sit here all day long counting turns as I analyze the motion. At the same time, it also kept the number of magnets required for the design to an acceptable number. First, I investigate the direction and rotational velocities. If I turn the handle 3 times, the first stage rotor rotates twice in the opposite direction, so the first stage rotational ratio hasn't changed. That also means that if I continue and turn the handle 21 times, the rotation on the first stage rotor would be 14 times in the opposite direction, and I would have made one full rotation on the output shaft. The second stage ring gear has turned 14 revolutions in reverse since it's tied to the first stage. The second stage pinion has made 21 revolutions forward since it's mounted on the same shaft as the motor. So relative to the ring gear, that pinion has made 35 revolutions. And if we apply the second stage ratio as before, 7/3, the output should give us 15 revolutions forward. That's relative to the ring gear, and since the ring gear is reversed 14 times, it gives us 1 revolution forward on the output. It sounds a bit complicated when you say it all like that, but it's really just relative motion. What we've established is that there's no difference in the first stage rotational ratio. The second stage also has the same rotational ratio as before. The only difference is that it now occurs in a rotating frame of reference. Alright, now what about torque? This is where things get interesting. Conservation of energy means that if my velocity at the input is reduced by 21 times, the torque at the output must increase by 21 times. That is assuming, of course, there's no internal losses. One major difference between this gear and the standard multi-stage gear is the fact that this only has one anchor to the base, whereas in the standard multi-stage gear, each stage had its own individual anchor to the base. Here I have the 2 stages of the ordinary multi-stage gear. I'm going to apply an engineering technique called a free body diagram, where if I have an applied force on one part, that force obviously has an equal and opposite reaction force, which I will indicate separately on the part that it interacts with. So starting with the pinion at stage 1, the motor, which I'm not going to show, is applying a torque. Let's assume it's a torque of 1 Newton meter, and it's in that direction. The direction of rotation of this pinion is in the same direction, and if the torque is in the same direction, it's a driving torque, and the pinion is absorbing energy from the motor. The first stage modulator is fixed, as we've seen before, and the rotor is rotating in the opposite direction as the pinion. In other words, the torque that it experiences is in that direction. And since we know the ratio between these torques, we know that should be 1.5 Newton meters. Newton's second law requires that the total amount of torque on this body is equal to 0 if it is not accelerating, which means the base must be supplying a counter torque that equals and cancels these two torques, so 2.5 Newton meters in the opposite direction. The applied torque on the first stage ring is in the opposite direction of its rotation, so it is losing energy to the pinion to which it is coupled. That pinion is experiencing a torque in the direction of rotation of 1.5 Newton meters, and it is rotating in this direction, it's absorbing torque. In this case, the second stage ring is fixed to the base, the modulator is the output, and it is rotating in the same direction as the pinion, which means the torque that the load applies on the modulator is in the opposite direction of its rotation, such that it loses energy to the load. And that value we've calculated to be 3.5 Newton meters. Since these two torques are not equal, but they do cancel out to some degree, it means that the base only has to supply an additional 2 Newton meters to give a total force balance. Before I look at the individual components of the compound differential gear in more detail, I'm first going to analyze it as a simplified single stage just to get the reaction force at the base. I know that the rotation and the input torque of the motor was in this direction, 1 Newton meter. I also know that the rotation of the output is in the same direction, which means that the applied torque by the load must be opposite to that, and it must be 21 Newton meters. The base must therefore be applying a balancing torque in this direction of 20 Newton meters. Now compare that to the reaction at the first stage base of the ordinary multi-stage gear, 2.5 Newton meters, and the direction is in the opposite direction. Again, looking at the individual stages in more detail, pinion 1 is getting a 1 Newton meter input from the motor. This pinion is also coupled to this pinion over here, so there could be a torque transfer via the shaft. I don't know how much, so I'm just going to indicate it over there. I'll try and find the value later. Let's give it a name. That is torque from pinion 2. The ring gear would also be experiencing a torque, maybe. Call that torque of ring gear 1. And the base is experiencing the same 20 Newton meter restoring torque. Right now we have an input torque, a reaction torque, and 2 possible output torques. So we cannot solve the externally coupled torque without knowing more. I can take this a step further and also draw in the internal reaction forces. The ring gear is experiencing a torque in this direction. In other words, it must be experiencing a reaction torque on this side in the opposite direction, since we know it's not accelerating. Same with the pinion. That torque must have a couple on the pinion side that is 1.5 times smaller, and both these torques would have reaction forces on the modulator, and I can then take that a step further and consider the modulator as a part on its own. It has a 20 Newton meter reaction force at the base, and it would be experiencing opposite and equal forces to these 2 torques over there, and that would be in that direction. I'll get back to this assumption about the individual components of the ring and pinion acting on the modulator ring, but for now let's assume it holds. What I do know is that the ratio between these must be 1.5. So the ring gear reaction must be 1.5 times more than the pinion reaction. I can immediately spot a problem here. The 20 Newton meter at the base plus the reaction due to the pinion plus the reaction due to the ring gear must be equal to 0 according to Newton's second law. My mistake was in assuming the torque direction. So this is the wrong direction. These are the proper directions. Now I can solve for the pinion reaction, and I can get that as 8 Newton meters, and from that I can also calculate the ring gear reaction, which is 12 Newton meters. This means I also have to go back to my first sketch, where I first made the assumption about the torque direction, and correct these torque directions. This ring gear torque is therefore 12 Newton meters, and the pinion is experiencing 8 Newton meters. Note the direction. This torque is acting in the same direction as the rotation of the ring gear. The torque on the pinion is acting in the direction similar to the motor. In other words, energy is being added to the ring gear. The ring gear steps that torque down to the pinion and drives the pinion together with the motor. Energy or power is not flowing out through the modulator to the outer ring. It's being pumped back into the system, so it must be coming from outside. And this is the first indication of the circulating power that I referred to earlier. I now have enough information to continue to the second stage. 1 Newton meter is coming in from the motor. 8 Newton meters is applied due to the magnetic interaction with the ring gear. Together, 9 Newton meters are applied to pinion 2. I know the modulator is turning in the same direction as the pinion, so it is experiencing a reaction from the load in that direction, and that value is 21 Newton meters. This second stage ring gear is transferring 12 Newton meters back to the first stage ring gear, and that would obviously make that a torque in the opposite direction. I'm just going to put it over here so that you can see the direction. That's 12 Newton meters. We've isolated and solved all the external torques applied to the second stage. All the external torques add up to 0, so we don't need any additional fixture to apply balancing torque. I can also look at this and analyze the internal torques. The ring gear has a torque coupling with the ring gear from stage 1. In other words, it needs to have a torque acting on it in this direction from the magnetic reaction with the modulator. Likewise, the pinion must be braked with a torque of 9 Newton meters acting in that direction, and together those two has a combined effect on the modulator which balances the applied torque from the load. Anyone designing a magnetic multi-stage gear need the values of these torque interactions so that you can size the gear for that specification. We've done it for the ordinary multi-stage, and we've also now done it for the compound differential stage. And as you can see, the torques involved at the interfaces are significantly higher than they are for the normal multi-stage. But then again, we are also working with a much higher output torque. I'm going to take this one step further and also calculate the power transferred at each interface. I know the torque and the direction and speed of rotation at each interface, so it should be pretty straightforward to calculate the power involved. This analysis will show how power flows, splits up and recombine to form the circulating power within the system. From that, it will also become clear what a massive impact that circulating power has on efficiency. This analysis really challenged my understanding of Newton's third law, especially when it comes to how you assign different forces when you pull apart a magnetic interaction involving more than just two magnets. I've chosen radians per second as my unit for speed simply because it makes it very convenient. I can multiply 1 Newton meter coming in from the motor and it gives me 21 watt. We've got a 21 to 1 reduction. That means at the output I have 21 Newton meters torque, 1 radians per second speed, and once again 21 watt output. For this analysis, I'm first going to assume no internal efficiency losses. During the torque analysis, I've already shown how the 12 Newton meters experienced by ring gear 2 in fact drives ring gear 1. Ring gear 1 drives the pinion via the modulator pieces, so energy, or power for that matter, flows backwards in this direction through the ring gear. The power going in this direction is 12 Newton meters multiplied by 14 radians per second. That's 168 watt. As this 12 Newton meters is stepped down through the modulator ring towards the pinion, we again end up with 8 multiplied by 21, and that is again 168 watt. That is what we expect if this coupling operates at 100% efficiency. I can therefore say that power effectively flows back into the pinion from the ring gear. At the same time, 21 watt of power is coming in from the motor via the shaft. That combines with 168, and we have a torque and power flow on the shaft connecting the two pinions of 189 watt. That can be confirmed by looking at the torque and speed at the coupling between the pinion and the modulator ring at stage 2. 9 times 21 gives you 189 watt. From a power perspective, it looks like we've pretty much solved everything. We've got 189 watt coming into the pinion, 21 watt is going out to the load, 168 watt is going back to stage 1. Somewhere in that coupling, the power split actually occurred. But just looking at the power doesn't tell us exactly how that happened. That 9 Newton meters experienced by the pinion must have a reaction force on the modulator ring. If that 9 Newton meters is multiplied by 1 radians per second, the speed of the modulator ring, it means only 9 watt goes from the pinion out to the load. Where does the other 12 watt come from? All I know is that 12 Newton meters and 186 watt is going back. If this was a mechanical planetary gear, analyzing the contact forces using Newton's third law is pretty straightforward. You will have meshing between the sun gear and the planet at an interface over there. You can then do the analysis at the interface where the teeth mesh with the ring gear. The two combined reaction forces on the planet transfers to the planet carrier, and that becomes the torque driving your load. There's a sequential contact between one component and the other. Every component only contacts one other component at a particular interface, and that's where magnets differ from mechanical interactions. In a magnetic interaction, there is no sequential coupling between one component and the next. Every magnetic particle in this interaction affects every other particle and is affected by every other particle. So you cannot split up any particular force into individual reaction components. The 21 Newton meters experienced by that modulator piece is a result of both these torques, and likewise this 9 Newton meters experienced by the pinion is a result of the magnetic field created by both the pole pieces as well as the ring gear. That means that this assumption of a 9 Newton meter reaction force on the pole piece going to the load is wrong, and I don't have to worry about how that 9 watt got split up from the 189 watt. This 189 watt coming into the pinion got split up simultaneously into 168 watt and 21 watt in one single interaction. When I started the torque analysis, my first foot in the door in solving any of the torque components was to assume that the modulator ring experiences a torque reaction component from the ring gear and pinion respectively. I really need to present this as one single reaction force to both the pinion and the ring gear, which exists because of the presence of the modulator ring. I cannot separate it into individual components. Fortunately, this initial wrong assumption about the components doesn't change the final result. The reaction experienced by the modulator ring is still equal to the total of the reaction forces experienced by the pinion and the ring gear themselves. Right, now what about efficiency? If this was a conventional multi-stage gear, and assuming each stage operates at 90% efficiency, you will lose 10% of the incoming power in stage 1, 10% of the remaining power in stage 2, leaving you with 80% going to the load. In this case, we have the power circulating, and every time it crosses one of these coupling interfaces, another 10% is dropped, and another 10%. And if you look at the values, this is 8 times the amount of power coming in. If the power has to circulate 8 times and loses 10% twice per cycle, it means the total efficiency would be equal to 90% to the power of 16, and that is only 18.5%. If the efficiency was 80%, your total efficiency would be 3%. Fortunately, magnetic gears are very efficient at low speed. If this is used in an application such as solar tracking, which is one of the things that the research paper suggests, where you have high torque and extremely low speed, we're talking less than 1 RPM on the output shaft, then the stage efficiency could be very high. And if it is the case that, for instance, a stage efficiency is 99%, you at least end up with 85% total efficiency. There is something else that you can do to improve efficiency. In this example, my magnet ratios are both very close to 1, and as it turns out, that actually results in an unnecessarily high times of the power being circulated. If you go to higher stage ratios, you can reduce the amount of time that the power circulates. If I can find a ratio that will reduce the cycle number from 8 to 4, I could get efficiencies of 43%, 17%, and 92%. So it's not all lost. Just as a side note, with the word differential in the name, it made me wonder if it's possible to design a differential such as the type used in motor vehicles. And this is what I came up with. It still needs a bit more refinement, but it's a topic for another video.